right, I'm going to make a video going over the probability assignment from Friday when we were talking about z-scores from Chapter 2 and Chapter 7. Um, this is how I'm going to give you feedback if the Google form requires you to upload images or if your answers are long paragraphs. I'll just make a video going over the problems. If it's a Google form where it's multiple choice or a quick answer, that's different. I'll just keep releasing the answers to you like I have been doing in the past, but this one I'm just making a video. All right, so we're going to start with number 1 here. We've got our IQ test. We are looking at scores for people over 16. They are approximately normal with a mean of 100 and a standard deviation of 15. So part A is asking what's the probability that an individual has a score of 110 or higher. So since it's just an individual, I don't need to do anything crazy. My mean score, it said, was 100, and my standard deviation was, what did it say? 15. All right, so I can just do a straight up z-score, the score that I'm looking at, 110 minus the mean of 100 divided by the standard deviation of 15. Round that z-score to 2 decimal places and you get 0.67. So this corresponds to finding the probability of getting a z-score greater than 0.67. Since it's a greater than, I'm going to have to do 1 minus, and then I need my z-chart, which I have down here, and I'm going to look for 0.67. So 0.67 is right here, which I get 0.7486. And when we subtract that from 1, we're going to get 0.2514. Now you can leave your answer as a decimal like that, or you can say 25.14%. All right, part B, now we're finding the probability that the average score for a simple random sample of 60 people is 110 or higher. So now when I'm writing this out, I'm looking for the average score of that simple random sample of 60 people, and I want to make sure that it's greater than 110. Now this is starting off similar, but this is now an average for those 60 people. Also, the thing that's going to change now is we have a sample size of 60. So we have to recalculate our standard deviation. The two formulas we have is that the mean of our sampling distribution is going to equal the population mean, which we were told is 100, so that does not change. But the standard deviation is going to equal the population standard deviation divided by the square root of the sample size. So the population standard deviation was 15, and I have to divide that by the square root of 60 because 60 was my sample size. And when you do this, you get 1.9365. I would leave as many decimal places as possible here. Now we're going to calculate our z-score. So again, I have 110 minus the mean of 100. But now this problem is different because my standard deviation is now 1.9365. Okay, and then my z-score I will round to 2 decimal places, and I'm going to get 5.16. So this is going to equal the probability of my z-score being greater than 5.16. Now when you go to look that up on your chart, you're going to notice that it's off the charts. Okay. Now, one way that you can think about this is in terms of a picture. If I have my normal curve, 0 would be in the middle, up to 3 standard deviations, but let's say we add more on. Okay, if we are at 5.16, we would be like right about here, and we're finding the probability of being greater than that. Okay, now my picture is not great. I need to fix my picture. Okay, sorry for the delay. Okay, so at about 3 standard deviations is where it typically will kind of drop off. So there's pretty much going to be nothing happening once you get past here. So if I'm finding the probability that z is greater than 5.16, there's nothing over there. So this would be essentially 0. So that's your answer to part B. Part C, find the probability that the sample of an SRS of 500 people will have a mean score less than 97. So I'm finding the probability that my mean score of my sample is less than 97. Now my sample size this time is, what was it? 500. So again, my formulas, my mean will remain the same at 100. The standard deviation will be the population standard deviation divided by the square root of the sample size. And again, the population standard deviation was 15. And if I divide by the square root of 500, I will then get 0.67 for my standard deviation. So when I go to do my z-score, I'm going to take 97 minus my mean of 100 divided by the standard deviation of 0.67, and my z-score will be negative 4.48. So I am trying to find the probability that my z-score is less than negative 4.48. All right, it's going to be off the charts again. So let's try to draw this picture here. Okay, so we're talking about a z-score of negative 4.48, somewhere right around here, and we want to be less than that. There's essentially nothing there. All right, and then part D. This time we're finding the probability for a sample of 5 people, and we're finding the probability that the mean score will be between 92 and 112. I don't know why the word more is there. I don't know if that's a typo or what, but we're looking for the probability that our mean score is going to be between 92, 92 and what was the other one? 112. All right, so again, the mean is going to remain 100. The standard deviation is going to change every time that sample size changes. So now we're dividing by the square root of 5. And our standard deviation will now be 6.71. And I have to find 2 z-scores, one with a score of 92 and the other with a score of 112. In both cases, we're subtracting our mean of 100, and we're going to be dividing by this new standard deviation of 6.71. So this first z-score is negative 1.19, and this z-score is 1.79. So I am finding the probability of my z-score being between those two. The smaller one goes on the left and the larger one goes on the right. And then when we use our z-chart, we look up this larger one first. So when you look up 1.79 on your chart, you're going to get 0.9633 minus, and then look up the smaller z-score on your chart, When you look up negative 1.19, you get 0.1170. And when you subtract those two, you get 0.8463. So 84.63% would be the answer to that question. All right, moving on. Okay, number 2. We've got a Gallup poll. It asked a random sample of 250 adults, have you ran a marathon? Suppose in fact 15% of all adults have run a marathon. Okay, now this is a proportion problem, and they just gave us the population proportion of 15%. Now, the formulas that we're going to need is that the mean of all of our sample proportions should equal the population proportion, which is what we were given. The standard deviation of our population proportions is going to equal the square root of p times 1 minus p over n. Now in this case, p is 0.15 times 1 minus 0.15 over our sample size, which it said was 250 adults. So when you type that in your calculator, we are going to get 0.0226. Okay, so kind of keep that in mind. We're trying to find the probability that less than 10% of the adults in the sample have ran a marathon. So I'm finding the probability that my sample proportion is less than 10%, less than 0.10. So I need to calculate a z-score for that. So 0.10 minus the mean of 0.15 divided by the standard deviation of 0.0226. That z-score should end up equaling negative 2.21. So this is going to equal the probability that my z-score is less than negative 2.21. Since it's a less than problem, I just look up negative 2.21 on my chart, and I get 0.0136. So that means 1.36% is my answer. That was the answer to part A, 2A. Here's 2B. We want the probability of being between 14 and 16%. So that's the probability that my sample proportion is between 0.14 and 0.16. Now, do I get to use all the same information? The probability that between 14 and 60% of the sample. Oh, the sample was 250 adults. So yes, I do get to use all this, this right here will stay the same because my sample size is 250. My population proportion is 0.15. So I will maybe just kind of rewrite that over here that we already figured these things out. This was 0.0226. Okay, so now I need to find my two different z-scores. Once when I have 0.14 and the other when I have 0.16. I'm going to subtract the mean of 0.15 from both of them, and I'm going to divide by my standard deviation of 0.0226 for both of them. And this first z-score ends up being negative 0.44, and this z-score is positive 0.44. So this is going to be equal to the probability that my z-score is between the smaller one, negative 0.44, and the larger one, positive 0.44. So I'm going to look up this larger z-score first on my chart. And when I do, I get 0.6700 minus, and then look up the smaller z-score on the chart, which is 0.3300. And you should make sure that you're able to look these up on the chart correctly. When you subtract them, you get 0.34, which is 34%. All right, 2C. Find the probability that more than 18% of the adults in the sample. So it's still the same sample, which is nice. So again, our mean was 0.15 and our standard deviation was 0.0226. So those are staying, so that's nice. And I'm finding the probability that my sample proportion is more than 18%, greater than 0.18. So let's get our z-score, 0.18 minus the mean of 0.15 divided by the standard deviation of 0.0226. We're going to get a z-score of 1.33. So this is equivalent to the probability of my z-score being greater than 1.33. Since it's a greater than, I'm going to do 1 minus. I'm going to look up 1.33 on my chart and I get 0.9082. Subtract those and you get your answer of 0.0918, which is 9.18%. Okay, now for the real question. So this, number 3, was an actual AP test question. So it, by nature, is just a little bit harder and a little bit more involved. So here we go. Okay, so Big Town Fisheries recently stocked a new lake in a city park with 2,000 fish of various sizes. The distribution of lengths of these fish is approximately normal. That's your clue that you will probably use z-scores. Big Town Fisheries claims that the mean length of fish is 8 inches. I'm just going to write that down. They're claiming that the mean is 8. If the claim is true, which of the following would be more likely? A random sample of 15 fish with a mean length greater than 10 inches. So a sample mean greater than 10 inches. Or a sample of 50 fish having an average greater than 10 inches. Okay, now this is more of a conceptual problem. So the idea is we have a population distribution that is approximately normally distributed. The mean is 8. Okay, now what's going to happen if my sample size is small versus if my sample size is large? My sampling distribution mean being larger than 10. So 10 would be over here somewhere. Let me change the color. 10 is over here somewhere. Okay, so being away from the true population mean, what is going to cause that? What is going to cause you to be farther away from the right answer? A big sample size of 50 or a small sample size of 15? So when you have small sample sizes, you are going to have more variability. This goes back to when we had a little dot plot on the side wall of our classroom. We had a dot plot that had a large sample size and one that had a small sample size. When you have small sample sizes, you have more variability, meaning your center might be a little bit off. If you have a large sample size, you're going to have less variability. Which means it'll be clumped more around the true mean. And the true mean in this case is 8. If you have more variability, things are going to be more spread out and not as close to the true mean. So when you have a small sample size, your average might be bigger than 10, which means it's farther away from the true number, 8. So this is more likely. When you have a small sample size, you might be off of what you should be at. When we have a large sample size, we would expect that our average would be closer to what it actually is, 8. So this is a more conceptual type problem. There's not really math to do necessarily. It's more logic, logicking your way through it. Okay, here's B. Suppose the standard deviation of the sampling distribution of the sample mean for random samples of size 50 is 0.3 inches. That sentence right there, if you don't read that correctly, you're going to get maybe a little confused. So remember our formulas. We have this formula and we have this formula. You really have to understand your symbols. This is the population standard deviation. And this is the standard deviation of your sample means. Okay, now the sentence here says the standard deviation of the sampling distribution of the sample means for random samples of size 50 is 0.3 inches. They're giving you that. They just gave you that the standard deviation for all of our sample means is 0.3 inches. So they did not tell you the population standard deviation. They gave you the thing that we ultimately needed. So we do not have to divide this by square root of n or anything. They gave us this instead of giving us the population standard deviation. So the common wrong thing to do would be to divide this by the square root of 50 if you weren't reading it carefully. So that's huge. And in this problem, the population mean we were told is 8. So we have the information we need, and we are trying to find the probability that find the probability that a random sample of 50 fish will have a mean length less than 7.5. So I'm finding the probability that my mean is less than 7.5. So I'm going to come and I'm going to compute a z-score. 7.5 minus my mean of 8 divided by my standard deviation of 0.3. That z-score will be negative 1.67. So that will equal the probability that my z-score is less than negative 1.67. And since it's a less than, I'm just going to look that up on my chart. And I get 0.0475. So 4.75% would be the answer to that question. So again, the wording here where it says the standard deviation of the sampling distribution of the sample means, that's what this is right here. So they gave that to you of 0.3. Had they told you the population standard deviation, then you would have had to divide that by the square root of the sample size. So it's the wording there that you have to be careful of. All right, 3C. Suppose the distribution of fish lengths in this lake was non-normal, but had the same mean and standard deviation. Would it still be appropriate to use the normal distribution to compute the probability in part B? Okay, so if it was non-normal, could we still do this problem? And the answer is all in, well, let's look at the sample size. The sample size was 50. And that's why we have the central limit theorem. Even if something's not normal, check your sample size. Our sample size is greater than 30, so the central limit theorem will apply. So I would say yes, we can still do part B because our sample size was greater than 30. Our sample size of 50 is greater than 30. So the central limit theorem will apply. Okay, something like that. So that is going over that Google form, and I'm also going to record a video on more probability stuff. Okay, bye.